Okay. Hello, everyone. Welcome to the topology seminar. Today, Baris Coskunuzer from University of Texas at Dallas is joining us. It's a great pleasure to have him here. So he will tell us about topological machine learning. So,
Okay, thank you very much for the invitation. So I'm going to talk about topological machine learning. So let me make a small survey. How diverse is this audience? So any CS, okay. Any undergrad? All right, okay. So don't worry. So you don't need to know anything about topology. You don't need to know anything about machine learning. That's a promise I am giving you. But if there is any question, just stop me and we can go from there. So basically, I'm going to talk about the applications of topological ideas in machine learning, some real life applications. And let me start with the main goal here. So the idea here is for the complex data, we want to use topology. And the main idea is data has some shape patterns and we want to extract them. So when I say data, I mean the three formats. Point clouds in high dimensions. You can imagine something like this. You can have like billion points in like 10,000 dimensional space, etc. And this is your data. And somehow this data, you cannot attack them with the usual methods, statistical methods, or some usual machine learning methods. And you see that there are some shape patterns and you want to extract them. And topology might help there. And the main idea is there are some shape patterns in the data and you want to find them. The second data format is going to be graph and networks. And this is one of the easiest way to get. So most of the relations, etc., like Twitter, every user is a node, and every connection, like if you are following something, you can imagine as an edge. This is going to give you a Twitter graph, or you can look at them. You can the heterogeneous graph like Netflix. Users are nodes and movies are another type of nodes, and then you are connecting them if they are watching them, and then you can make recommendations there. Those are some graphs, and there are lots of good real life applications there, and we want to use topology in some of them. So this is the picture, and images, of course. So in every image you can see some shape patterns. So in many of them topology is not very useful, but in some of them it is really helping a lot, and you are going to see which ones I am talking about at the end of this talk. Okay, so topological data is a 20-year-old field, 25 year maybe, but in the last 10-15 years it has many applications in very different fields. Today I am mostly focusing on the medical side, but you can see lots of papers in many different domains using topological machine learning. Okay, so we want to find this shape patterns in the data. That's the idea. So let me give you some dummy example. So we can see two different point clouds here and the plane. It's very simple. And intuitively, we see two small circles in the left and one large circle in the right. That's just an intuition. There is nothing there. There is no circle, of course. This is just a set of discrete points. But I can see somehow a large circle in the right and two small circles in the left. How can I distinguish them? That's today's question. So I see them, but I want to get a formal mathematical output so that I can use in my problems. So all topology background unit is in the following slide. So today I'm going to use. So when I say topological feature, I will talk about only zero-dimensional features, one-dimensional features, and two-dimensional features. I'm not going to go about two-dimensional features. When I say zero-dimensional homology, I am talking about the connected components of the space. So if you look at here, the first one, I see 6 bullets. So I'm going to say the rank of the zero homology is 6. There are 6 pieces. How many pieces do I have? This is the zero-dimensional homology, and rank 6 is the dimension of this. All I care how many pieces I have here. And one-dimensional topological features are the holes, and one-dimensional homology captures them. Do I see any hole in this space? No, there is no loop, there is no hole. So the one-dimensional homology is 0 in this one. In the second one, everything is connected. You can go from one point to another point with a path in this space. This is a path connected space. So the zero-dimensional homology has rank 1. There is only one piece. But if I look at do I have a hole here? Yes, I have 3 holes here. So the one-dimensional homology has rank 3 here. Now let's look at this one, the brown space, like a simplicial complex. If you look at here, it's all connected. So the zero-dimensional homology has rank 1. And let's count the holes. So I have 1 hole here, 1 hole here, 1 hole here. I have 6 holes, and I am going to say rank 6. But there is a question, do I count these other loops here? If a loop is filled with some disk or something like that, which you can construct a point in the space, so I am not going to count it. They are fake ones. So I am just only considering the loops which is not bounding anything. This is the hole for me. So I have 6 holes here, but this circle does not represent a hole in this space. It's a circle, but it's not a hole. And 2-dimension is something similar. Let's say this is a hollow sphere. Okay? Now, it's one component, zero-dimensional homology has rank 1. And there is no hole here. If you have a circle, you can bound it with a disk. Then I'm going to say one-dimensional homology has rank 0, but it has 2-dimensional cavities. I'm going to count them as 2-dimensional homology. So this is all you need to know for today's talk. 0-dimensional means connected components. 1-dimensional means just holes, loops, which you cannot contract to a point in the space. And cavities are the rank 2 homology. Okay, so the basic idea here is if your data has similar shape patterns, so you have 1,000 patients, for example, you have some point cloud data or some graphs. Let's say 500 of them are normal and 500 of them are like sick, and then you want to say if 500 of them, the normal ones, have same topological patterns, I'm going to call them in the same class. So same data, same class data should develop similar topological patterns. That's the main intuition here. They should have some similarity in the patterns. Next question is, okay, how can I capture them? How can I write them down, the topological patterns? So the tool is called persistent homology here. So main idea here is you give me data. It can be a point cloud, it can be a graph, it can be an image. I'm going to produce a sequence of topological spaces, most of them simplicial complexes, a sequence of simplicial complexes induced from the data. And I'm going to keep track of the topological changes in this data, in this sequence. And persistent word comes from if a topological feature persists along this sequence, they are the dominant ones, and they are basically coming from the data, and it is basically tells us the topological patterns in the data. So persistent word is important here. And let me give you some explicit examples. Okay, so you can consider persistent homology as a 3-step process. The first step is the most important one, and depending on the data type, it changes. So now, right now, I'm going to talk about point cloud, but I'm also going to talk about graph data, and I'm going to talk about image data. This construction is going to change. How can I induce some meaningful sequence of topological spaces, a sequence of simplicial complexes from my data? And then I'm going to record them, the topological changes. This is called persistent diagram. In a minute, I'm going to show it to you. And then I'm going to convert them into some nice vectors. Let's see this simple example. So I have 14 points here. Okay. This is my space. I'm going to give you some sequence of topological spaces. Now, so the main intuition for the persistent homology comes from the following idea. So if you look at this point cloud from very far away, you cannot distinguish nearby points. And if you look at very far away, very far away, you won't see the point cloud, you will see the silhouette of 2 circles, basically, because you cannot distinguish the points. So I'm going to create this idea by using a dual approach. So instead of going from far away, so I'm going to change this. So nearby points, you cannot distinguish them. I'm going to just add some disks around them. So imagine for every point, I have a enlarging disks. Let's say radius 0.1, 0.2, 0.3, and I'm just taking unions of them. So if you look at here, I have 14 points. That means in 0 dimension, I have 14 components. I'm going to write them down. This red ones represents my 0-dimensional topological changes. 0.1, 0.2, and when I reach 0.5, I am enlarging the disks. And the union, it's no longer 14 components. Some of them merged along the way. 1, 2, 3, 4, and 5. There are only 5 components when I increase the radius of the disks here. Along the way, some of them merge with the other ones. You can see they died. And I am just continuing with these 5 components. I continue to enlarge my disks. And when I hit 0.7, for example, all of them get connected. So when I take the unions of the disks with 0.7 radius, this yellow space become connected. Okay? Now, after that, I have one component and it will live forever. You cannot reduce one component, it's going to live forever. So this is going to go all the way. And these red guys are zero-dimensional homology. My zero-dimensional persistent barcode, basically. Let's go to the loops. I don't see any hole here. But when I hit 0.7, I see that this large circle emerge. There is a hole in my space. I am just marking this number, 0.7 scale. I see a circle. And at 0.9, the second circle emerges, the small one. And I continue to enlarge it at 1.3. This guy gets filled. It's no longer a hole, it died. And I continue to enlarge this. At 1.5, I still have this circle, but at 2.5, this large circle also dies. And this is called persistent barcode. The red ones are zero-dimensional persistent barcode. The blue ones are one-dimensional persistent barcode. So my the sequence of topological spaces are these yellow guys. So I have 25 steps. I am only showing you 5 steps here. This is 0. 0.1 is the union of 0.1 disks, 0.2 disks, etc. And along the way, there are changes. You can see them here. And at the end of the day, I have this persistent barcode. So I only care about the initial points and end points. Initial point is called the birth time. End point is called the death time. So the whole information can be condensed in here because to describe an interval, you only need the endpoints. So you can describe them in the x-axis is going to be birth time, y-axis is going to be death time. All the points here, for example, this is starting at 0.7, ending in 2.5. I can put a point here to describe this bar here. So this is persistent barcode, but this is called persistent diagram. They basically have the same information. Yes?
Why are there only 7 red dots?
No, you don't see all of them because they are all. Yeah, you can count them with multiplicity if you like. Yeah. They are all started at 0. They are all in the y-axis. But this is forever, infinity. The other ones are, some of them are in the same time, so you just have multiple points at the same time. Yeah. Oh, okay. There is okay. So that's the next question. So how do you use them? So you have 2 different data. You have 2 different persistent diagrams. They are completely useless because they are points in the plane. So how are you going to measure them, the distance between them? This is called optimal transport distance. You have a matching, and then by using this matching, this is called Wasserstein distance. So you do the best matching, and then you look at the distances there. But again, so persistent diagram, as you suggest, is not very useful. I'm going to talk about it, but I want to just point out something else here. Now, I put this diagonal here, and that diagonal is always there. Why is that? Because the diagonal represents points like 2, 2, 3, 3, 4, 4. And in the persistence diagram, this means all topological features who was born at 2 and died at 2 with lifespan 0. They are trivial topological features and they must be there. They always consider them. So if something even is, it's like a null set for persistence diagram, but they are basically telling you anything on this diagonal is trivial. Now, by looking at this persistence diagram, which one is more important? This guy or this guy? That's a good question here. So if you are closer to the diagonal, your lifespan is smaller because your y minus x is value is smaller if you are closer to the diagonal. That means you are a less important feature for me. The longer ones, this is the persistent ones, are more important here. So if you are away from the diagonal, those guys are more important for me. Okay. Now, I got my, okay, I start with point cloud. I got the persistence diagram. So what's next? I have some machine learning problem. I have some real life problem. How can I use this persistence diagram? Most of the time, this is really useful, not very useful. Why is that? Again, I have 1,000 like histopathological image. 500 of them are sick. 500 of them normal people, and you want to develop some machine learning output for this. Now you have 500 persistence diagrams here, 500 persistence diagrams here, but they are just subsets in R2. Just subsets. You cannot take average of them. You cannot do any statistics on them. That's why to be able to use them with machine learning effectively, the third step is called vectorization. From this persistent diagram, you want to get some vector or functions. Imagine you have 500 functions here for the normal people. You can take average of them. If you are close to your average, then you can call them, those guys are normal guys. And if you have like 500 sick people, 500 functions, you can take the average of the functions, you can do statistics on them, and then you can play with them. So this is much more useful for machine learning purposes. So how do you convert a persistent diagram into a vector? There are lots of tools. I'm just giving you simplest two. The simplest one is called Betty function. Question? Oh, okay. So let's say this is my barcode. I am only counting the number of alive features in each interval. 0 to 1, I have 2. I am just marking these 2. 1 to 2, I have 3. 2 to 3, I have 3. 3 to 4, again 3, 3, 3, and 2. This is my Betty function. How many alive features at given threshold? That's it. You can consider this as a vector too, 7-dimensional vector with the input 2, 3, 3, 3, 3, and 2. Okay, I converted this into a vector. I lost lots of information. The long bar does not appear as a long bar anymore. Just alive feature is the given threshold. Yes, but in many cases, if your small features are more important in the downstream task, Betty function can be very useful, and we are going to see this today. A more important vectorization method is the following. You take these 4 points in the persistent diagram. You take these right triangles. Now, remember, if you are away from the diagonal, you are more important feature. And if you are away from the diagonal, this right triangle will be larger. You just rotate them 45 degrees, and you'll get some like mountain silhouette like this. So after you get this, the largest guys will give you a function for each point. Second largest guy will give you another function. Third largest guy will give you another function. You can look at them and you can use them as a vectorization of the persistent diagram. It's not a very strong vectorization, but it's a very simple one. Yeah. This is like every persistent diagram comes with its dimension. So 0-dimensional persistent diagram, 1-dimensional persistent diagram. You get all of them and you use them. And you can convert them into vectors too. Like this is a function, but you can convert them into vectors. Now this looks very dummy, and let me show you some examples. Oh, this is the flow chart for CS people. They like this kind of flow charts. You give me data. Next step is get a sequence of simple complexes. Depending on the data you have one of this. And then there are lots of software libraries getting your persistence diagrams very easily. And then you just use vectorization. And then you use these vectorizations in supervised or unsupervised learning. We'll come to that. So I'll give you 3 examples in the remaining time. So how can you use this idea in real-life problems? The first one is from 2015, a shape recognition question. This one. Okay, let's look at this, guys. I give you 4 3D shapes. This is a paper from 2015. You can find the details in here, subsampling methods for person tomology. And that's a very nice example of how TDA works. So I have 4 animals, and you are just looking at the surfaces of them. They are hollow. There is nothing inside. And on these surfaces, you just randomly choose 500 points representing that animal. You fix them. These 500 points, you fix them. Now, I am going to produce my synthetic data out of that. For each animal, I make 100 subsampling of 300 random points out of this 500. So I have 300 points, 100 times for each animal. I have 400 point clouds. 100 of them corresponding to camel, 100 of them corresponding to, all of them have 300 points. And this is coming from this subsampling of this 500 points. Okay? So 400 point clouds. 100 of them corresponds to camel, 100 of them corresponds to lion, 100 of them corresponds to flamingo, and 100 of them corresponds to elephant here. Now, let's look at their persistent landscape, the vectorization I just showed you, this one. For each animal, I have 300 points. For each point cloud, I have 300 points, subsampling from these 500 points of the surface. And I have 100 of them, and I'm just randomly looking at this. So this is the important picture. Green guys, there is a band here. The middle dark green stuff is exactly the average of the all persistent landscapes coming from flamingo ones. We have 100 flamingo persistent landscape, 100 of them. 2. This is dimension 2. Because you can imagine here this is the most important dimension is 2 because you have hollow structure. So you have this. When you have this thickness of the band is a 95% confidence band. 95% of this 100 persistence diagrams lives here. They are very close to this median curve. And blue guys are representing the lion persistence landscapes. The red guys are representing the elephant ones. And camel guys are here. You see here. A very different shape structure. Now, let's go back and let's appreciate this. If I give you this 400 point class in A, and I am trying to get some structure, some method to distinguish them. For some reason, you see the differences visually, but how can you distinguish them? So topological data analysis gives you a very effective method to distinguish them. Simple persistent diagrams and then the persistent landscape. These vectors are really distinguishing them. So if you give me a new one without telling me, by looking at its persistent diagram, a persistent landscape, I can tell you which one it is. If it's closer to this one, it's an elephant. If it's closer to the other one, it's going to be a lion, etc. Okay? This is point clouds. An example for point clouds. It's very useful for shape recognition. Again, there is a complex data. You see that the shape is playing a huge role here. How can you get that information out of the data? Yes.
Instead of applying this to three-dimensional shapes, could we have used it for 2 or higher than 3 dimensions?
Yes, any dimension you can do that. Yeah, but again, so in some dimensions it may not be useful. So the information can be trivial. So you should check all dimensions basically most of the time. Okay, so second part of the talk is about how to use topological machine learning in image setting. And we are going to look at the histopathological images of cancers here. So this is a paper from 2023. Yeah, yeah.
So does this depend on the distance you take from the light? Would it consider two lions as same if they're photographed from different?
No, no, no. That's a very different question. So I have only one lion. I have fixed 500 random points. This is a very special question. Now, your question is very different. This is also a very important question. So if a person is doing this or doing this, can you distinguish them? So what same person, different shape patterns? So that's a very different question.
Even here,
Yeah.
maybe even if these four things would be the same.
No, no, no. You fix 500 points. You fix 500 points at the beginning, and then you make 300 points first, and you randomly choose another 300 points. So these are two different representations of the lion, and the landscapes are person landscapes are very close to each other. Yeah, it's a very specific problem, but I mean it tells you what the story basically. Now the motivation of this project was so histopathological images are very important for cancer detection, and every time you have a pathologist, but using AI machine learning can be very effective to help them to distinguish, to prioritize the important cases by using this machine learning algorithm. These are called clinical decision support system. The idea is you are not going to replace directly the pathologist, but you can significantly improve their productivity by giving a score at the beginning of each image, and you can tell them these guys must be looked right away. These are very important, and these guys should be prioritized. And I don't see any problem in these other ones. You can just look at them later. So if you prioritize them, you can make them very fast, and then you can help them a lot with your scores here. That's the idea. So you are trying to get some good machine learning algorithms to help the pathologist here. Now, here is, so again, it's all about the filtration method. How do you create a filtration in the image setting? Now, an image like this is histopathological, and the dimension of this here 2000 by 1500. This means you have 2000 times 1500 pixels, small boxes. Okay? Now, this is a color channel, color image. Each pixel have three values, RGB values. R is red, R is red channel, G is green channel, and B is blue channel. And they are all from between 0 and 255. 0 means black, 255 means white, darker to lighter. Now, what I am doing here is I'm going to create a cubical complex. I'm going to show you the dummy example later, but let me see what it means. So here, for example, I fix red channel, and in here I am starting with completely blank image like this. So I start activating some of the pixels. So for example here, if for any pixel, if the pixel value is smaller than 90, I am activating them, meaning I am making them black. This becomes a black and white image, binary image. And then next, I am going to 120 threshold. I am activating them. I am getting a black and white image, and then it goes on like that. It will be completely black at 255. And let me give you this. Okay, so this is also a grayscale image. When I look at this, I see this. There are lots of numbers around, 0 to 255. Every pixel value has some color value. Now, let's look at this toy example. This is the most important slide for this part of the talk. So what do we do here? So you have a 5 by 5 image, and every pixel has a color value between 1 and 5, let's say. Okay? Every pixel has a color value between 1 and 5. In X1, I am activating all pixels whose color value is smaller than or equal to 1. I have these guys. You can see them. And how many components do you see here? 1, 2, 3, 4, 5. With the 0 vector starts with 5 here. Do you see any loop here in the black, guys? No loop, it's a 0. Second image, I am activating everything up to 2, 1 and 2, and I get this binary image. Now, if you look at this binary image, how many components do you see? 1, 2, 3, 4, 5 again. This is 5. And I don't see any loop in the dark regions. Again, 0. Let's go here. X3 is my third step in the filtration. I am activating all pixels up to 3. I got this binary image. Now, how many components do you see? One component here. This is all connected. I have 2 components. So beta 0 third entry is 2 here. Now, do you see any loops? Yes, I see loops now. One loop is here, one loop is here. So it's going to be 2 for the third entry. And one more. It's all connected. You can see it here. It's going to be 1 component. But I see 3 loops now. This is 3. So this is the beta vector. Now what did I do here? For this image, I get 5-dimensional beta 0 vector, 5-dimensional beta 1 vector. And when you concatenate them, it's a 10-dimensional vector here. This is very, very important. This is the heart of the machine learning. In the machine learning, in any case, for mathematicians, the idea is very simple. All these deep learning algorithms or all convolutional neural networks, graph neural networks, NLP, they are all doing the same thing. You give me any data, image in this case. So 1,000 images. Okay, 500 abnormal, 500 normal. For each image, you get 10-dimensional or 100-dimensional vector representation. So any image is now a vector, image x, vx, r to the 10, let's say. Now you have 500 normal, 500 abnormal, r to the 10, let's say. You have blue guys everywhere and red guys everywhere. So red guys represents abnormal guys and blue guys represents normal guys. So during training stage, you define a decision boundaries. This is a blue region, this is a blue region, this is a blue region, and this is red region, this is red region, and this is red region, whatever it is. So these parts are red region. Now, let's say this is my training set. Now you give me 10 new patients. Okay? So let's say Y1, Y2, Yn. Now these guys are, you are looking at their vectors now, 10-dimensional representations. If it goes here, I'm going to call them normal. If it goes to blue region. If it goes to here, it's going to be blue region. If it goes to here, it's going to be blue region. And if it goes to here, it's going to be red region. So the vector representations are the key. If your representations are strong, if you are separating your normal class and abnormal class very well, then your machine learning algorithm is very strong. Because at the end of the day, you give me an image, my algorithm will map them into a 10-dimensional space, and where it lands is going to tell me what kind of image I have. It can be a graph, it can be a text. They are all converted to some sort of vectors like this. And your machine learning algorithm is trying to find best representations, best vector representations of your data like this, and then making the best decision boundaries for that. This is all we want. And topology, by just summarizing the topological patterns like that, it gives you excellent topological representations, vector representations like this. In some of the cases, they are working very well. This is one of these examples. So how does this work? Okay, this is an example of how we get this. Now, for any so we look at 5 different cancer types. All histopathological image, we are looking at the tiles like this. For each image, we get 8 color channels. Red, green, blue is already there. Their average is grayscale. If you have like red, green, and blue numbers, you just average them, it's called the grayscale value. And there is also another color coordinate system, HSV. We also use it because a priori, we don't know anything about the disease. We don't know what's going to work. In some color channel might be much more useful than the other one. So we have a very large basket. We are putting everything we can find about the image into that basket, and then we are going to let the machine learning algorithm to choose which ones are useful and which ones are not. So that's all we want. If we put them there, the machine is going to find what is useful for us. Okay, 8 color channels. And for each one of them, we compute BT0 and BT1 vectors. We use like 50 thresholds or 100 thresholds, I don't remember. And then if you are using 50-dimensional threshold, you have 50-dimensional BT0 vector for each, and 50-dimensional BT1 vector for each. You have 100-dimensional vectors here. Now, so this is a very important picture. Whenever we start a project, the first thing we look at is this picture. What does this say? So for bone cancer, you see here, there are 3 types in the images. Like we have like 15,000 images, 5,000 of them non-tumor, 5,000 viable tumor, 5,000 non-viable tumor, let's say. And these are the BT vectors, BT0 vectors. You see the different, and the dark green guys are the median of these guys. And dark orange guy is for non-viable tumor type, you see this 40% confidence band. And when you look at them, there is a very distinct pattern. And when I see this picture, I am 100% sure my model is going to work, because in that level, I can see the separation here. They have different. So if they are very close to each other, then topological patterns are not distinguishing. But if they are creating a very distinct pattern like this, I am 100% sure my points are going to land very different places for each class. So and this is the BT1 vector for bone cancer. And again, you can see very different structure. Colon cancer, something like this. Normal tumor stroma, etc. Cervical cancer, this time HSV vectors work very well. And prostate cancer and breast cancer. So in 5 of them, they all you see all these separations. Now what we did here is we get 1600 dimensional topological. So we use 100 dimensional threshold then. So 100 dimensional threshold, 2 vectors, BT0 and BT1, and 8 color channels gives you 1600. And we also use the earlier models, local binary patterns and Gabor filters. We put them into a basket. We have 28 dimensional features for each image. So you can look at them as a 2800 dimensional embeddings. You can think of them as a very large number. And you are right, this is a very large number, and most of them are correlated. Means they are basically repeating the same information. You don't have extra information. Most of them are useless. We know that. But we don't know which ones are going to work. That's the point. So to eliminate the useless ones, but you can do the following. So we just look at when we increase the number of the best number, you can choose the best features in your machine learning model, and then you just increase the number of features you are using. Until 500, I see some steady increase, but after 500, there is no increase in the performance, accuracy performance. That means you have only, for each disease, you have only 500 basically good choices here. So we cut them at the 500. Means for each basket, I will have a filter. I'm just going to eliminate 2300 dimensional features. I'm just going to use the useful ones. Why am I doing this? So main reason for that in the machine learning, if your features are useless, meaning, so let's say you have some numbers are very close to each other. All the time, first entry and second entry are very close to each other. So there is no extra information, but you are just increasing the dimension of the space. They are useless dimensions. So I give you 300 dimensional, so I give you 500 dimensional information in 2800 dimensional space. Your machine learning algorithm cannot work very well. If you eliminate them in this 300 dimensional space, if you give the information in the smaller space, it can work much better. We know that. So this is called feature selection. And we are going to choose the best 500 features here. Oh, yes, that's a very good question. Most of the machine learning algorithms, when they are doing this training and test training stage, in that stage, they are always they are using some features for their algorithm. So they are for example, XGBoost has a feature, has a like option. It is giving you the importance score of every feature he is using, every dimension. So you can look at them as a dimension. So if two classes are very separate from each other in one dimension, that's a very important guy. But if they are in the other direction, they are very close to each other, you cannot separate them. I cannot use this one. So I cannot put a hyperplane between them, basically, something like that. How close to each other these classes are, how do you use them? So importance feature is, I guess, importance score or something like that in XGBoost. But most of the algorithms have that, yeah.
So the machine learning algorithm takes as the input like the coordinates of these.
Okay, so that's another question. Now, okay. At the end of the talk, I'll give you a much more example, much better answer. Now, convolutional neural networks, for example, that's the machine learning algorithm. CNNs are, you give them image, they are doing both jobs. They are getting you 128 dimensional embedding for each image, or 64 or 256, depending on what you want to do. And then for each image, you are getting an embedding. But this is the best embedding it can get for a downstream task. And then it is also defining the decision boundaries. They are doing the both job. So vector representation is also learned in the convolutional neural networks. In my case, I am giving the topological embeddings of them. After that, I am using machine learning. You can use the machine learning in the first stage too, vector representation. And graph neural networks are also doing this. So in the graph neural networks, for any graph, you are trying to find 64-dimensional vector, for example. And then MLP part is just doing the decision boundaries for you. But finding this good embeddings, so you give me 2 classes or 3 classes, you want to separate them. If your embeddings are separating them very well, then you did your job.
So by separation, you mentioned this hyperplane. So
Yeah. Separation means this. Exactly as you imagine. This is a good separation. You don't have to have one cluster, but you can have 5 clusters. But as long as you can separate them, that's a good separation. This is a good separation because you see the decision boundaries clearly here. Something like this. What is a bad separation? Bad separation is exactly this. You don't see any clear separation. They are all together. More boundaries. It's overfitting, basically. Overfitting means you are just using the training data and you are getting excellent results for training data. But if I get to the real life, you have no idea what's going on, basically. The decision boundaries are very weird here. So this is not a good embedding, for example. You cannot separate them. So of course, you can always find for the training data a good separation like this. For each point, you can have a small ball, and then there's a good separation. But is it going to work in the real life? If I give you a new guy, just I wish you best of luck so to get the right answer. Okay? All right, so this is number of features. 500 is a good number. This tells us. Okay, this is basically the idea. For each color channel, we get 8. For each image, we have 8 color channels. 16 persistent diagrams, 1600 dimensional topological features, local binary pairs and Gabor filters. We put them together and then we choose 500 of them. And this is our final embedding for each image. And we run MLP on them. So these are the data sets. Where am I? Where is there? Yeah. Okay, you can see it here. Now You can see it here. I am only using topological embedding some XGBoost or MLP. So you can see that these are very strong results, and we are getting very close, and some of them we are passing them. These are accuracy results. And I want to show you one more picture. Okay, this is an ablation study. If I only use grayscale images, not red colors and blue colors, etc., only grayscale, I got this first column, first row. You can see that if you use all colors and all features, you can bump your accuracy 6%, sometimes 15%, etc. So the other colors also have very useful information, so you need to choose them wisely. Yes?
For evaluating this accuracy of different
Yeah.
methods, did you use string test?
Yes, exactly. So most of the time what you do here is you take like 10,000 images you are given with annotations, with labels. You are choosing 8,000 of them, keeping the class ratio. And then you are training the model here. And you don't see these 2,000 guys. After that model, you are creating your embeddings for new ones. Your decision boundaries will tell you it is yes or no. It says abnormal. And then this is your accuracy results. Yeah, 80-20. In graph learning is most of the time 10-fold CV, but in medical imaging it's usually 70-30 or 80-20. Okay. You can combine this. So these are vectors at the end of the day. Topological vectors is a vectors at the end of the day. And there's a very dummy way to combine with the CNN guys. At the end of the day, CNNs are also creating some vectors. You can concatenate them and run MLP on them. This is a very simple method. These guys are giving you 128-dimensional vectors. Topology gives you 200-dimensional vectors. When you concatenate them, you get 328-dimensional representations of them. Is it going to work? I don't know. Let's check. In many cases, we see that they are helping a lot. And then they are, so this is the original CNN method. We use ResNet probably here. And this is when you concatenate them, you see in some cases, you see like 8%, 9% bumps. So topology gives you some complementary information to convolutional neural networks. But let me be honest here. So this is ResNet, but when we run with the Cihan transformer, in 2D images, we don't see basically no improvement, like at most 1-2%. Cihan transformer is a very strong vision transformer, and they are making. So it turns out vision transformer always captures them. But in 3D images, topological embeddings are working much better than existing deep learning methods. Because in 2D images, we are very fine because we have a very, very large training data. When you train any convolutional neural network with some ImageNet, etc., billions of images, it becomes very smart. But in 3D, we don't have this kind of annotated data, and it's a big problem. So they are strong, but they don't know what to do, basically, because they don't have training data in 3D. So okay, MRI images, for example. So brain MRIs and everything. You know, these are all 3D images. Yeah. Okay.
But you have this time dimension, time duration.
Oh, fMRI is 4-dimensional. MRI is 3-dimensional. You just take a static image. So you have voxels this time. So you can imagine your whole brain is 150, 150, 250 dimensional box. Every pixel has some grayscale value. So like rectangular box. But if you have fMRI, then you have time dimension. That's a 4-dimensional image. So, okay. Now, okay, so if you still have some energy, I'm going to graphs. How much time do I have? Usually, at this point, I don't have too much time.
Let's see, I think 7 minutes left.
7 minutes?
Yeah,
okay.
We started a bit late.
Okay, let's make it 17 or just kidding, yeah. I'll try to wrap this up as fast as I can. So, okay, drug discovery. This is a very interesting problem. So how do you use computers in drug discovery? Usually you have some sickness or problem, disease, etc., and you want to develop a drug, but you don't have the manpower to test that in the wet lab. So you have a very good idea what's going to work, but you cannot choose which ones to work. So there are 10,000 potential compounds, but you cannot test them in the wet lab. You want to reduce them to 200 compounds to test them in the wet lab. So at this process, you are using computers, and it's called virtual screening. You have a very large compound library, and you want to find the highest potential 200 guys so that you can test them in the wet lab. So at this point, we come to the scene, and then we want to find a good model to predict the most highest potential drugs. And what is a drug? You have a protein. It is causing the problem for you. It can attach to another protein and make you sick, or it can attach to another cell. You can make you sick. So proteins are very large molecules, like 1,000 atoms, etc., and they have some three-dimensional shapes. The three-dimensional shape is not the important part, but these hook regions are the important part. So all these proteins have some gaps like this, and then by using them, they can attach to another protein, or they can attach to another cell and make you sick. And what's a drug? Drug is a small compound, like 20, 30, 40 atoms here. That small compound is binding your protein exactly at this place and preventing them to cause the problem, hooking into the other protein or hooking into the cell. So you want to fill this gap with small compound. So you are trying to find a small compound in the right shape, and when I inject into the person, it can find the place and then hook itself. This is the drug. So you can still have this right shape, but if it's not going to the right point, then it's not a drug. So this is the big problem. So for the shape case, we are using topological data analysis in the following way. So there are two approaches. One approach is try to understand the active region in the protein, the gap, and then try to find the right shape. That's a computationally very heavy and hard problem. But the other one is called ligand-based method. For some reason, for the proteins, you know, like 5, 10 compounds likely to work, right shape, and then you have like 100,000 potential compounds, and you are trying to find the most similar ones to these positive samples, 10 positive samples. So this is basically, you are trying to rank all the 100,000 compounds for the similarity of the 10 positive guys. So you just want to find the similarity here. And there are lots of good methods here. Morgan fingerprints, etc. I'm just skipping this because I don't have time. What we do here is why we are using topological machine learning. Basically, for any graph, I'm going to find you like 10-dimensional or 20-dimensional vectors, giving you a good idea what's going on. So this is an example. I am not using 3-dimensional structure for molecules because there's a big problem with the 3-dimensional structure. You have the every atom's coordinates here, let's say, but single bonds are always rotating. And any molecule does not have a stable structure. They are always changing shape. So even though at one time it's in the right shape, another time the conformation is a different shape. So you have to check all the conformations, and you want to get this. That's why we are going for 2D. In 2D, we have graphs. Every node is representing an atom, and every edge represents a bond. Okay? Now, the good thing here is, every node, I know what they are. This is a hydrogen. This is a carbon. The white ones are hydrogen. The gray ones are carbons. Blue ones are nitrogen, and red one is oxygen, whatever they are. They all come with some their specific properties. Now, how am I going to use topological machine learning? Remember, in point class, I use this enlarging balls for a sequence, topological spaces, and I just kept track of the topological changes. In the images, I use cubical complexes. Remember, the color thresholds are changing, and the binary images are changing. My binary images are my topological spaces. Now here, I'm going to do something else, which is this guy. So let's say I have a graph, and every node comes with a value, and every edge comes with a value. So only one of them is also fine. So for the nodes, I am going to use the upper part. So G5 means I am activating every node whose value is smaller than 5. So let's look at them. I only see 2 nodes. If there is an edge between them, put them. I get this subgraph. G10 means I am activating every node whose value is smaller than 10. I see these guys and I am activating them. I get a sequence of subgraphs like that. For edges, I am doing the same thing. G5 here, I am activating every edge whose value is smaller than 5, and I am also always adding their nodes to them. And at 7, I have these guys, and I go on like that. So these are called filtrations, graph filtrations. I get a sequence of subgraphs. Now, I can count the number of components, I can count the number of loops in them, and why are they useful? Remember, I gave you a molecule. Every node comes with a number, atomic number, for example. I am involving my chemical information exactly in my filtration diagram here. Every bond comes with a strength, single bond, double bond, triple bond, and aromatic bonds. These are giving you also H values, 1, 2, 3, 4, and then you can directly involve them in your filtration sequences. And when you get them, we use, for example, we know both information are useful, we are using bifiltrations here. At this point, I am skipping lots of technical details. It's called multi-persistence, and multi-persistence theory is widely is incomplete because of commutative algebra. We can talk about this is another subject for another big talk. So, but you can still vectorize them in some dummy way. So we are doing that, basically horizontal slicing. Anyway, so we use these vectors, filtrations, H filtration, node filtration. H are coming the bond strength. Node values are coming from atomic numbers. You, for example, here in this guy, I got 2 values. How many components do you see? 3 components. Beta 0 component is going to be 3. There is no loop here. It's going to be 0. And then I get 4 by 4 matrix, beta 0, 4 by 4 matrix, beta 1. That's a very simple way to do that. And so you don't expect this to work, I know, but interestingly, it works very well. There are also lots of technical details, biotorestrics, filtrations, etc. So we use 2 different methods. Random forest, which is a very simple model, tree-based model, and we use a few-shot learning model called triplet loss in this vision transformers. So remember, I gave you 4 by 4, but it's indeed 20 by 20 matrices. You can consider them images, and you can use convolutional neural networks on them. Anyway, so our experiments show that in one small data set and in one large data set, we do the following. Okay, what are we measuring here? I am not measuring an accuracy here because you give me 10,000 components and you give me 10 samples, for example. My all guesses are not important. Only the best ones are important. So I am only considering my best 100 guess, for example. How many of them are true hit? So you are comparing this to random chance. How much do you increase? This is called enrichment factor. Okay? So 1% enrichment factor only cares about your first 1% guesses. And if you are multiplying the random chance bit by 20, your enrichment factor is 20. That's the idea. And we see that you use this topological vectors with random forest, you are beating all the state of the art. State of the art means all the deep learning methods, etc. in this problem. If you use vision transformers and triplet loss, you are getting even better results. Now, by the way, if you are using enrichment factor 2%, you can enrich at most 50 times to get the 100%. If you are using enrichment factor 5%, the most you can get is 20%, and 20 times. So these are the values. This is the large data set .E, and again, our model is random forest. This is very surprising for us too. Beat all of them. In the other one, you have only a few data. That's why the deep learning method worked very well. But if you have enough data, random forest works very well. Okay, so you can find all the details in our paper, and I'll stop here. Thank you very much.
Okay,
Questions? Any questions?
Yes.
So what's like a useful heuristic for when you should use TDA for a problem or when it's
Okay.
like a definitely will not
Yes, yes. So, for example, minis dataset. When I see that it's complete, TDA is completely useless. Do you know what minis dataset is? Any computer vision people, the first thing they learn in the digit ones. So TDA completely useless there because handwritten digits. Okay, this is your image. This is a 7. This is a 2, but you don't expect topology to separate this because there is only one feature, and this is very, very hard to guess what is going on here. So maybe a 1. So you cannot expect topology to get a work here. So what do you expect? Before we start this histopathological problem, I was 90% sure it's going to work because of the following. So a pathologist see a tumor, right? And then say there's a tumor here. Now, when you are developing tumor, you expect that in a smaller scale, there are some color changes. You cannot see them, but in the background, there must be some other changes. Very small features. The beta numbers representing these very small features. So if you look at this picture, the numbers are real numbers. So what do you see? 500 small dots. In viable tumor, if you go to 150 threshold, you are seeing 500 dots. I don't see them, but my algorithm is seeing them. So in the binary image, you really have 500 components. That's not easy to see, but your algorithm is seeing that. So what is the intuition here? When you are developing the tumor, you must have some discoloration in the other scales. It's smaller scale, but there are something here, the changes. For each class, you see these changes. And these numbers are 800, for example. You cannot see 800 components there, but my algorithm can see it. So if there are like very complex patterns, you can expect topology. Otherwise, you cannot expect topology to work because what is your persistence diagram here? There are only 1 or 2 dots and they are very close to each other. You cannot do anything there. But here, your persistence diagram is doing something like this. This is your persistence diagram. And you are expecting something like this. The density of the small dots are very different for classes. They are very close to your diagonal, but the density is very different because it is some of them are changing in like 100 threshold, but some of them are changing in 130 threshold a lot. That's the clue here. Yeah.
Yeah, but I don't think it's very clear sometimes because when you were showing the animals,
Yeah.
I would have thought a priori that the animals should not be very distinguishable because you've got 4 legs and a big body. Okay, the flamingo no, but the rest of them kind of.
So why do you think this is happening? Because you see this hollow part in elephant and this one. So what is the elephant? Let's look at the elephant. These red ones are elephant. How do you interpret this? Let me see. The 4 guys are here. Okay, so what you can imagine, I don't see some. There are 2 big peaks here. Okay, elephant is not easy to interpret, but the camel is here is easier to interpret. Somehow, it creates a very big hollow after some threshold. You are filling these guys up. So when you're enlarging the balls, after that you're only left with this guy. I don't know what is happening with elephant, but I need to look at that.
The reason I bring it up is
Yeah.
because I don't know. When I look at those numbers, they also it just seems like you're also capturing some geometric, not just topological.
No, yeah, this one is geometric completely.
Yeah.
This is a like viatory strips filtration basically. I skipped that part, but basically you are trying to understand. So my earlier talk is exactly about this, like a year and a half ago. So the length of the persistence bar exactly tells you how hollow it is. So imagine your BT2, the second dimensional person, and you have a very large bar. Start here, and then you are enlarging balls, and then you are filling them up after very late time. So it means you have a very hollow region. So the length of these persistent diagrams, the peak points basically, tells you how hollow you are. That's the geometry here. Yeah. Yeah. Yeah, it is achieving something, but distinguishing 1 and 7 is really, really tricky for this. Yeah, because topological, okay, so there is, you don't disturb for topology, so you cannot distinguish a mark from, what was it? Donut, yeah. So topologically they are same. So basically you cannot distinguish this because I mean topology. Okay, so geometry and topology are two different things. Geometry is basically sizes, curvature, etc. Topology does not care. So a big ball and small ball have the same topology. Basically, they are homeomorphic. They are exactly equivalent to each other. So we cannot very fine distinguishing it because our tools are components, holes, and the cavities here. We don't care about the sizes basically. If you have a cavity, it's there. But because of how you are changing the sequence, you can track the sizes of them because of the sequence, how you build the sequence. Other than that, for sub-level filtration, because, for example, like the graph ones, you don't measure any size because the filtration, the sequence, has nothing to do with the graph's length or etc. It's just activating some of the nodes. Now, not every persistent diagram is about the sizes, but if you are building like this, via two-strip filtration, the length of the bars are exactly about the size of the topological feature. Yeah. Yeah. Yeah.
Maybe previous to this, there was a flow chart.
Yeah.
I don't remember which slide it was. Just, yeah, here. So do you have any sort of idea for what's like the computational bottleneck, which of these steps?
Okay. Okay, computational bottleneck, that's a very good question. The filtration type is the key here. Now, what I showed you for graphs are the sub-level filtration, and it has no computational cost at all. So, but at point cloud, if you are in a very high dimension, and you feel like even though you have sparse data, it can be very complicated. Okay, because, okay, let me show you the picture. I lied to you because since you are asking for it, we always work with simplicial complexes. What is a Beatrice complex? I cannot work with the unions of balls. You cannot compute the homology of them with computers. You always need a discrete object. What we do here is, so the blue stuff is exactly what I am looking at. These unions of balls. But I'm going to give you a simplicial complex out of it with the same topological feature. Now here they are all disconnected, right? Whenever they touch each other, I am putting an edge between them. Okay? So I increase my thresholds, radius, and whenever I see a triangle, I am putting a triangle between them. If I have a tetrahedron, I am putting a tetrahedron between them. Not squares, but triangles, so 2 simplices, 3 simplices, and 4 simplices, and go on like that. And I'll get a simplicial complex out of it. Now let's look at this one. How many holes do you see in the blue space? 1 and 2. How many holes do you see in the simplicial complex version? And remember, these guys are 2 simplices, and you feel them. 1 loop is here, 1 loop is here. This is called Neuer lemma. This simplicial complex is homotopy equivalent to this kind of all homologies are same. And you continue like this, you get your simplicial complexes. Now the computational bottleneck is here. The dimension of the simplicial complexes can be very, very large. Why is that? Because all you care is your pairwise distances. If 10 points have this same, say smaller than some threshold, the pairwise distances, then you have 9-dimensional simplicial complex. And it becomes very big simplicial complex. So, but for the
if I have the radius large enough, all of a sudden all of them are in here.
it's going to be a complete graph. And that's going to be a very messy stuff. But when I go back here, in image, you don't have any problem. In 3D sometimes, but in 2D, you have no problem. Cubical persistence works very well. The simplicial, as long as your space is like a cubical complex, then images have no computational bottleneck in 2D, and 3D you can manage it. In graphs, there are two types of filtration methods. One of them is very similar to point cloud. That's computational, very, very heavy. It's very informative, but it's a nightmare for many people. But sub-level filtration, I just show you, it's very friendly. Yeah. Mm-hmm. Yeah.
Complexity, so would it be too hard to compute like cup product information so that you can separate the donut here and
There is cohomology too. Yeah, persistence cohomology also. Yeah, they are doing that.
so you can compute cup
Yes.
product and it doesn't much add
I mean,
complexity.
the big problem, the big question in machine learning, is it worth it? Okay, if it's not helping you, so cup product is very special, you know, and it is very distinguishing very specific spaces. Do you really, want to go for it? If you have a very delicate problem and topology is really, really informative, you can do it. But in most cases, you have some idea, but you don't know if it's going to work. And you don't, most of the time, you are not very sure topological features are really, really strong to be able to do this. So you are trying the usual methods first, but if you need something more delicate, you can always go for it.
How about three-dimensional topological features?
Yeah, you can do that too, but I've never seen them. I've never seen them. So I am a geometric topologist, three-dimensional. I am always working with three-dimensional, but I've never seen an example. Three-dimensional topological features are used. So this is my domain. Exactly. All my life I did three-dimensional manifolds, but I've never seen it used in it. But I've seen two-dimensional, but I never seen three-dimensional. It might be useful, but when you get higher dimensions, the computational bottleneck is becoming very large. So people are not trying it.